This is an A-level Further Mechanics 1 question on elastic springs. A particle P of mass m is attached to one end of a light elastic spring of natural length A, a modulus of elasticity kmg. The other end of the spring is attached to a fixed point O on a ceiling. The point A is vertically below O such that OA is 3A. The point B is vertically below O such that OB is equal to half A. The particle is held at rest at A, then released and first comes to instantaneous rest at the point B. Show that K is equal to 4 over 3. Okay, now I've taken all the information that's in the question, I've put in a diagram. So we've got the ceiling here, this is the point O, a mass of m on this light elastic spring, modulus of elasticity kmg, natural length A, and it's held at this point A, which is a distance of 3A below O. It's released from rest, so zero velocity, and then it first comes to rest, so zero velocity again, at the point B, which is a distance of half A from O, and we have gravity acting downwards. Now this is an energy question, and the three types of energy we need to be considering are elastic potential energy, also gravitational potential energy or just potential energy, and kinetic energy. And the way that I do these questions is I look at the energy at the start and the energy at the end. If there's no energy loss by work done against friction, and there is none in this case, then the energy at the start will equal the energy at the end. If there is energy lost by work done against friction, I need to subtract that from the energy at the start to get the energy at the end. Right, so energy at the start. So basically this is the energy at A. How much elastic potential energy is there, gravitational potential energy, and kinetic energy. So we'll start with the elastic potential energy. Now the formula for that is lambda x squared over 2L. So lambda is this kmg. X is going to be the extension. Now if the lateral length is A and it's at this point, which is 3A, the extension is 2A. So lambda, we've got the extension is going to be 2A, and that's all squared over 2 times the natural length. So that's 2 times A. Now I can simplify this down because I'm going to get 4A squared here, and if I divide that by 2A, I'm going to be left with 2A, so it's going to be 2A kmg, and that's it. There is no denominator because they've cancelled out. So we've got the elastic potential energy. Right, gravitational potential energy, or just potential energy, remember that's mgh. Now what I'm going to do is to take this point at the bottom here and take this as the point of zero potential energy, just to make things easier. So zero height. So the amount of gravitational potential energy is 0, and the kinetic energy is also 0 because it starts from rest. Yeah, we're told that in the question, released from rest at A, so no kinetic energy. So at the start, the total energy at A is just going to be 2A kmg. Right, so let's just highlight that because we'll need that in a moment. So energy at the start. Right, so now let's look at the energy at the end. So that's the energy at B. So what's happened at B? Right, let's have a look at the elastic potential energy. So same formula, lambda x squared over 2L. So the lambda is still kmg. Now this time the spring is in compression. The natural length is A, it's now half A, and it's being compressed by half A. So x is half A, and it's going to be half A all squared over 2 times the natural length, and that's going to be 2A again. Let's look at the gravitational potential energy at B. So it's now gone up by a particular height, and the amount of height it's gone up by, it's gone from 3A below to half A. So it's gone up by 2.5A, an increase of height of 2.5A, which you can write as 5 over 2A. So gravitational potential energy mg, and the increase in height is this 5 over 2a. I guess I could write that as mga or 5 mga over 2, and I guess I could simplify the elastic potential energy while I'm at it. So what am I going to have here? A quarter a squared divided by 2a. So I'll have a quarter divided by 2, which is going to be an eighth. The a's, or one of the a's, is going to cancel out, so I'll have 8 at the bottom, and I will be left with kmga in the numerator. And kinetic energy, because it's when it comes to instantaneous rest, that is still going to be 0 as before. So let's have a look at the total energy at the end. So that's going to be these added together, and let's do that to see what we get. So if I take out the k as a factor, so I'll have mga over 8. Take out the mga as a factor. That would be better, wouldn't it? So I could actually take out mga over 8 as a factor when I add these together. So that will give me k, and then plus, and we're going to add 20, because if I multiply this by 20, that'll be 20 over 8, which gives me the 5 over 2. Okay, so this is the other bit I want to highlight. Using the conservation of energy. Yeah, I don't think you need to state that, but I will anyway. So using conservation of energy, energy at the start equals energy at the end, so I'll have 2a kmg is equal to mga over 8 times by k plus 20. And what I want to do is to rearrange to make k the subject. So before I do that, I can divide both sides by m and g and a as well. So I'll get 2k, then if I expand the brackets, that'll be plus k over 8, or minus k over 8 if I bring that to the other side, and that's going to equal the 20 over 8, which is the 5 over 2. That will give us 15 over 8k is equal to 5 over 2. Divide both sides by 15 over 8, and that gives k is equal to the 4 over 3 as required. Part B, find in terms of g the acceleration of p immediately after it is released from rest at A. When you see acceleration, that means forces. Now what forces are we going to have? So we'll have tension, the tension in the spring pulling it up, and its weight going down. So the equation of motion will be T minus mg is equal to ma. Now T is equal to lambda x over L. So the tension is going to be lambda, so that's going to be 4 over 3 mg, because we worked out the k, so 4 over 3 mg. The extension of the spring, natural length is a, so the extension is 2a, so times by 2a, divided by the natural length, which is a, minus mg is equal to ma. Now I can cancel out the m's because every term has an m in it, and these a's are going to cancel out as well. So what we have is 8 over 3g, so 8 over 3g minus g is equal to a. Now we're fortunate, this is something I just want to point out, that the a's did cancel out, because we've got A for length of spring and we've got A for acceleration. So it may be that you decide to use a different letter for acceleration. So I'm just going to use the capital letter A, because what I don't want to do is confuse the little letter and the big letter, but they did cancel out anyway, and I'm sure that was done purposely so that there wouldn't be any confusion. Okay, so if I do this now, so we've got 8 over 3g minus g, which leaves A, our acceleration, equal to 5 over 3g. Okay, so there's our answer for part B. Part C, find in terms of G and A the maximum speed attained by B as it moves from A to B. Now, the maximum speed occurs when the particle is in its equilibrium position. So we want to find that position where the particle is, or what the extension of the spring is, when it's in its equilibrium position, and that will happen when the mg and the t are equal. So we have t equal to mg. Now t, that's that lambda x over L. So lambda, that's 4 over 3 mg lambda. Now the extension in equilibrium position, we're just going to call E divided by the natural length, which is A, and that is equal to mg. And what we want to do is to solve and find E. Now we can cancel out the mg's from both sides. So now what we've got, and I'll get rid of my little diagram here, don't need that anymore, is 4/3 E over A is equal to 1. So we have 4 over 3 E is equal to A, and then E is going to equal to 3 over 4A. So we now have the extension in this equilibrium position. We are now going to be using energy, using that equilibrium position, to work out what the speed is. So what we're going to do is going to look at the energy at A and make that equal to the energy at the equilibrium position. So we have energy at A is going to be equal to energy at equilibrium position, and they're going to be equal conservation of energy, because no energy is lost in this case because there's no work done against friction. Right, so let's start with the energy at A. So remember, 3 types of energy: elastic potential energy, gravitational potential energy, and kinetic energy. Now at A, there's no gravitational potential energy or kinetic energy, just elastic potential energy. And we actually worked that out in part A. So that's going to be our lambda 4 over 3 mg, and then the extension squared. Now at A, the extension was 2A, because remember natural length is A, so we got 2A extension, so 2A squared over the natural length, or 2 times the natural length, 2A. So that's the energy at A. Now we're going to look at the energy in the equilibrium position, and in fact there's all 3 at the equilibrium position. So let's start with the elastic potential energy at this equilibrium position. So we've got lambda 4/3 mg. Now we want the extension squared. Now the extension is what we worked out here, 3/4 A. So lambda extension squared, so 3/4 A squared, over 2A, 2 times the natural length. But we've also got gravitational potential energy because it would have moved up from A, and we want to work out how much it's moved up. Now this is going to be mgh, how far has it moved up. Now we need to be careful here, because the extension is 3/4 A. So how far up is it? Well, the natural length is already A. We've got this extension of 3/4 A. Okay, from the top, we need to know this distance here from the bottom. Okay, how much has it moved up? Well, if we do A plus 3/4 A, that gives a distance of 7/4A, and we need to subtract that from 3 to find out this height increase. So 3 minus 7/4 gives us a height increase of 5/4A. So 5/4A. Okay, what else have we got? We've also got kinetic energy here because we're trying to work out the speed. So that'll be half mv squared, and we want to rearrange this and solve for v. Right, now, are there any things that can cancel out where every single term has got m in it? So let's cross those out. So we'll cross out all of the m's, and we'll try and simplify this as much as we can as we go across. So here we're going to have 4/3 times by 4a squared divided by 2a. So let's simplify this. So 4/3 times by 4a squared will give you 16/3, or 16/3 a squared, and that's going to be divided by 2a. So 16/3 a squared divided by 2a, and that all simplifies down to 8/3a is equal to, and we'll try and do the same thing here. So we're going to have 4/3 g times by 9/16a squared, and that's going to get divided by 2a. I'm sorry, I forgot to put in the g here as well. So this should be ga. So 4/3 times by 9/16 divided by 2 is 3/8, and we'll have an a squared, and we'll have an a that cancels that out, so we'll have 8/3 ga. Then for over here, the next term, we'll have 5/4 ga is equal to half v squared. Right, let's start rearranging it to make v squared the subject, or v the subject. So you've got half v squared, and that's going to equal to 8/3 ga minus 3/8 ga minus 5/4 ga. Right, so doing that leaves us with 25/24 ga. Then what we'll do is we'll times both sides by 2, so v squared is going to give us 50/24 ga, and lastly we'll square root both sides, so I guess that'd be 50/24 ga. Let's put that on the calculator, see if that simplifies a little bit more, and it does. I guess I could leave the answer like this, but we'll get 5√3/6 and then root ga, and there are other ways you could write it. You could put all of the g and the a underneath the √3 sign, but basically that's the speed, maximum speed, and as I said, occurs at this equilibrium position, and we needed to actually work out the equilibrium position before we could use energy to find out this speed.